Hello everyone. This is Lab 6 subroutine parameters and returns. Basically, parameters and returns are um, function parameters and how the function returns values. So inside a function, when you call myfunc, or let's say it's an adder function. When you call add, and inside the parentheses in your C, um, you can say A through like ABC. So it'll be add parentheses A comma B comma C. So usually what that it does, or how that is formatted for you guys, is that you're going to use all those three values or parameters and you're going to add them up in certain ways, and you're going to output something from those three parameters, and your function will return a certain value or a value that you need for your project, function, program, whatever it may be. So today we'll look at parameters and how to return from those functions. What we've been looking at from the past labs is basically functions without any parameters or returns. So it was usually a void function, but in this case now, with Lab 6, you'll be able to do a little bit more complex parameters and be able to return certain things from those functions. Now, like I stated, this is actually a C code, and from your computer science 111 courses, you should be familiar with how to write functions. So in this case, we have this int find turn speed, and inside it are your parameters. You do some stuff to get something out of these parameters from this return right here. So we're going to learn how to do this, adding parameters and adding how to return specific values from your functions in this lab. And, this is calling this function right here and using the values from turn and other things. So there are two methods, but method one is passing these parameters by using registers. Now this, please keep in mind, this is an Intel syntax for assembly. This is completely different from what we've been using. We've been using the AT&T assembly syntax. They're sort of similar, as you can see that it's like a push D instead of a push L. Your registers are pretty much the same, but I just want to show you an example of how parameters are passed into your functions. So method one is using general purpose registers. So your general purpose registers are your 4 ABCD registers. You can use those registers, store something, and push it through to use these functions or use these parameters inside the functions. So we're using the EAX register to pass through parameters into this function. Oh no! This this loop right here. So a comment about the general purpose registers and how your compiler uses your general purpose registers to store parameters. So by default, your GCC compiler uses the stack to pass parameters into the stack. That's by default. But method one is a very unique approach to get parameters. You're just essentially skipping that step. You're just skipping the stack step. what we've learned in Lab 5, and then directly storing parameters into registers, in this case A or D, register D, to utilize those parameters. And there is a specific syntax that you have to type in the terminal command line before you or you compile, and that's given to you in the lab manual. You're not required to know that specific command line to pass parameters into registers directly. But just to let you know, this exists, and that you can skip this whole stack step and just go directly into the registers. The advantages of using method 1 is that you don't use the stack. There's no access to memory, so you don't have to travel from the CPU to RAM and then from RAM to CPU. When you're using the stack, that's what you're doing. But the disadvantage is that you have a limited number of registers. I mean, you can force it and use all 9 registers that you have, but most likely you're going to use those 9 registers for different things. And by using method 1, you got to really keep track of caller responsibilities and then callee responsibilities. Now, for our assembly assignments, while you don't need to understand and know the direct command line of calling and storing parameters into registers, that concept of using general purpose registers as parameters will be used in your lab assignments. That concept will be very visible in doing caller responsibilities and callee responsibilities. Excuse me. So the reason why we do that, and we had you do that in Lab 5, was solely because of this, to get you familiarized with all this parameters, being able to access and store stuff into the stack. And while this method 1 doesn't use the stack, it is a I want to say a microcosm of the big picture of how it is stored and utilized. But just scratch that. Just know that there is a method of using general purpose registers to pass parameters directly to the registers. It skips the whole stack process, but that's just not a very popular method. Method 2 is using the stack. So you can push, you can't directly push values in. You got to push registers into the stack. But by doing that, you're pushing this value inside the B register into the stack. But anyways, I digress. Again, this is a Intel syntax, not AT&T syntax, so please keep that in mind. But this is pretty similar. There's a caller responsibility right here. You're pushing the B register and A register. We're assuming that there's parameters stored inside the B register and A register, and you do the call to the function, and then this I will explain later, why you subtract or add to the stack pointer register. But you go inside your function. You want to do the prologue, procedure prologue, and then you want to grab what you stored with this, and then start manipulating those parameters to do what you desire for your function. This is much more of a common step than method 1. The advantages over using registers is that you can do way more parameters. you don't really have to have a full mastery of, understanding what the caller wants to do and then the callee wants to do, and then the function is in C always uses the stack. As I said, this is the default method. Your GCC compiler always goes to the stack. How to use the stack for parameters? You just simply push the parameters onto the stack from the calling function. Remember that it's going to be in reverse order by convention. So in the callee, remember how the stack is rearranged in the prologue. You have caller responsibilities and stack frame, and access the parameters by an offset of the EBP register. This is basically pointer notation. That's how you access parameters, local variables. You should really be familiar with accessing local and temporary variables that you used in Lab 5. If you are still having questions about that, please email me so I can work with you with those subjects. Moving on. So this is me explaining reverse order, how it's pushed in reverse order. So normally in C language, your parameters and your functions are as such, function 1, A, B, and C. In assembly, what pushed in reverse order means is that you push the last one first. So you push LC, push LB, push LA. You can't really do C, B, and A. You got to move LC to a register and then push that register in. But this is just a little overarching sort of example for you guys to understand. And then you could do the call function 1, and then you do the prologue, and then you can grab A, B, and C from the EBP register, and so on and so forth by using the EBP register. So now, where in assembly does this get returned? So in this function, we want to add these three numbers together, and we want to output the result. In C, we use a return statement, and it just returns the value to this variable right there. In assembly, the return value is always placed in the A register. So EAX, AX, AL, and AH. That's that. Always the A register. Now, remember, EAX, AX, AL, and AH, it depends on the byte size of your number. So if it's an integer, remember it's this. If it's a character, it's either of these two. It's just how you place them. AX is kind of like an odd man out. It's 16 bits. So it's kind of weird. It's a word, but I digress. So subroutine parameters. This is how, when you call, I want to specify, when you do this C first. So in your assignments, you had a driver file, a C driver file. And then in the assembly language, you wrote what this function was. So let's X this out, and then let's imagine our C driver file calling this function with A, B, and C. When your compiler runs, it'll automatically push these three values in reverse order, C, B, A, into the stack. So it'll be C, B, A. It'll push C, B, A into compiler stack. And then you call this function. When your C file is saying function with parameters, you're storing this parameters into the stack, and then you're calling this function now. So that means you have to do the return address, the next line of this function right here, the return address there, and then you start with your prologue. So you push the EBP, push EBX, move EBP, to ESP or vice versa, or what, right here, move ESP to EBP, and then you subtract 12 from ESP to make spaces for your local variables. So that's your prologue. And then when you do move 12 EBP to EAX, EBP is pointing here. 12 is 3 spaces, so 1, 2, 3. You're accessing parameter A, so you're moving parameter A into EAX. This is going to be a number. And then you want to add 16 from EBP, so it'll be 4, 8, 12, 16, B, 2 EAX and storing, same thing. The next line, and you're storing everything into EAX. And so you're adding all these 3 parameters. In this example, you don't need a local variable, but if you want to be safe, or if you're using a recursive step or problem, whatever. But if you are doing a recursion, you are going to need a local variable space to store this result back into here. And then so when you invoke your function again, it'll set up a new prologue right here, up here, and then it'll start setting it up. After that, in this example, we don't really need local variables. Anyways, so your ESP is like right here. You move the EBP where the EBP is pointing to. So you move 24 into ESP, which makes the ESP point here. And then you pop the old EBX into EBX, the old EBP into EBP, and then boom, you're pointing to the return address. Voila, you're done. Now, what do we do with these parameters here? Before I get into that, just remember, result is placed into the A register. That's why we're doing this. So, what do we do with this parameter right here? Because after this call, let me go back. After this function, you're going to still do more things. You're going to do more things down here. Let's say, scratch that. We're doing, instead of 2 files with a driver file and an assembly language file, you can write both of these in one assembly file. This little example right here is basically doing one assembly file, combining both of these basically. That's why you're doing push C, push B, push A, and call function 1. That's encompassed all here in this line. Your compiler, when doing both, is saving you a ton of time by already automatically pushing these values in for you and doing the call for you. But let's say we don't have a driver file, we got to do this from scratch. So we have all of this, and then we have more that we want to do down here. So we write more code after call function 1. Now, so inside main, you would probably set up a prologue. You don't really need to set up a prologue, but anyways, you're still probably going to use the stack after this call right here. And if you are diligent enough to keep track of your ESP pointer where it's pointing right after it exited your function right here. So it runs this function, goes to the next line, and you need to execute more function or more code. So you have these 3 parameters kind of getting in your way. You're done with these parameters. So you gotta quote unquote clean up these 3 parameters to get to stack space that is not function 1. Right? So every time a prologue or a function is invoked, you have a specific stack space allocated for that. So this stack space So right here, this stack space is for this function. Right here, this function 1. But for your main, you will most likely have a stack space down here, way down here. So you'll probably have more parameters down here. So it's like a nested function. You can think about it like that. You got to be able to access the right values here, but these 3 parameters are getting in your way. You want to kind of get rid of them, but remember, you can't delete anything in the stack. You can only replace. So this, clean up the stack. It's very simple. You just have to add to the ESP. And in this line, we're doing add 12 to ESP. What it does is ESP is pointing right here. If we add 12, it's going to be 4, 8, 12. And it skips all these 3 parameters to kind of start in the appropriate stack space. So that's why we have the add 12 in ESP here. In the the Intel syntax, they did a sub 8 because you only had 2 parameters. So if you have 3 parameters, 4 times 3 is 12. So you manipulate the space by 12. You have 2 parameters. It's 2 times 4 is 8. So just keep that in mind. You have AT&T syntax, so it's add 12. That's why we add 12 to ESP, and then we can start doing whatever we want from the, assuming that we have EAX stored, the value stored in EAX, and we haven't messed with it. We can move it to D. Right here, move it to D. So this is if you are done with these parameters. If you still need to use them, you can't just add 12. You got to just pop it back out into the appropriate registers so you can use them, just like callee responsibilities and caller responsibilities, a LIFO syntax. But don't forget that, but keep that in track. And so you have A register, the result in your A register, so on and so forth. Now, a comment about your function headers. Now, you will need to put arguments and returns into your function headers. If you guys don't do so, that'll be minus 5 points. It'll be easy 5 points to understand what arguments are going in and what your function is outputting. It tells me a great deal about what you understand. Remember, it returns. You can't just put returns A register. You gotta say a specific thing, like what does it return? And in this case, it's D. So likely think of it like this: where is A getting stored? Okay, so this is just a re-evaluation of the find turn speed function, 2 parameters, return. And so this is written in C, but we can translate this to assembly. This will be stored into the stack. All this is done, and it'll be returned in the A register, and then the A register will be moved into a turn speed to get this out. Now, a comment about this dot global A to I. I think this was your first lab assignment. Then you had a dot global A to I, and then a dot type A to I at function, and then the label A to I, and then prolong. So, so dot global is saying it's a global function. There's 3 different types that you can write, but just understand it can be like dot object, dot no function, I believe. More detail will be in your lab manual. Please read through it. But we don't require you to understand or memorize the different types. Just understand this .global A to I function name is declaring that the function is global, and you can call it anywhere. And then the .type is specifying the type of that function. So this is pretty obvious, but it's saying at function. So you're establishing that type, that dot type A to I, and that this label is a function, but it can be like an object, at object, or at no object. There's different types, but now you understand and know what these things are, so you are required to write these things from scratch in your Lab 6 assignments. Now, Lab 6, it's computing factorials when one integer is passed through. So learning how to program factorials, how to compute factorials by inputting a parameter like 3, and it'll compute 3 factorial, and it'll output that and print that output. There's little structure given in the specification code, but go through line by line. If you just start line by line, and then kind of converting what that line specification code, in your specification code, what that line is supposed to look like in assembly, I think that's a good place to start, and your program has to be recursive. Otherwise you're going to run into a lot of memory problems. I mean, even if you do this recursion mode, you'll probably run into a lot of seg faults, but learn how to use the GDB debugger to get through the seg faults. That's that. Please ignore this date. You're going to have a quiz 6 next week over subroutines and parameters. I don't know if T evaluations will be up, but and then after quiz 6, your final exam will be given on Friday. Please email me if Friday is a bad time to take your final exam. I will give you 2 hours to finish your final exam. I'll give you 1 sheet of notes to have for your final exam. I trust that everybody did their labs diligently and without relying too much on this lab solutions, because the final exam will have a coding portion to it. So the first half will be just fundamental things about assembly, much like the quizzes questions, like what's the importance of learning assembly? What are the 6 different addressing modes in assembly? Those types of fill in the blank, matching, so on and so forth. And then the latter half of the assembly is code. You have to write code. Now, it is a very extensive code. A lot of people have struggled with the coding portion of the final exam. But if you didn't rely on the lab solutions and you understand how to write all these lab assignments, then you should be able to do this coding portion in the final exam without any problems. It's divided up into, I believe, 8 different sections. Question 19 is just a long explanation of what the program specification is, but there's nothing to be written in question 19. You skip to 20 through 27. It's broken up into 8 parts. The question 20 will ask you about, I think, the prologue. I mean, I'm not 100% sure, but one question will be about how to write the prologue. Write the prologue. One question will be write the epilogue. One question will be how does the stack look like? And then another question is how do you do a specific part of this coding assignment? And then you're never going to be asked to piece all those things together, but they're going to ask you specific sections of your programming specifications, and you just write a partial code. That's what it is. So that is your final exam. If you have any questions, please let me know. All right. This is a neat little quote. C is glorified assembly. Anything you can write in C can also be written in assembly, but you can do a lot more complex things in assembly. In assembly, your code owns your computer. So that's a direct reference to memory and being able to manipulate memory directly. But yes, that concludes Lab 6. And if you have any questions, feel free to email me. Otherwise, have a good rest of the week. Thank you.